Stiamo per andare online in streaming su YouTube. Stiamo per andare online. Okay, we may get back, continue in explaining and discussing the modeling procedure. Today, we will introduce a fundamental concept, which is that of model conceptualization. And then we'll give some hints on the verification step. Okay. I already told you that this is the point, model conceptualization, at which you decide which is the complexity of the model that you're going to employ. We discussed a little bit the term of complexity. We said that in this context, complexity may be seen as a characteristics of an environmental system from one side, but it might be seen also as a characteristic of a model describing the particular system that I'm looking at. The point is that of finding a right trade-off between a realistic detail in the description and elegant simplicity in terms of computational demands. We start by trying to make a description of the system in a steady state. This means that we start by doing a steady picture of the system. And in this context, we try to decide which is the most appropriate hierarchical level. So the point of finding a trade-off between realistic detail and the simplicity is reduced to that of finding the correct hierarchical level of my description. For example, the graph here describes the correct placing in a hierarchical level of a eutrophication model. So if our focus is eutrophication, we want to study process of eutrophication. The point is that if we want to make a consistent description, we shall also include the upper hierarchical level and lower hierarchical level. So, for example, in terms of space and time scale, we may increase the spatial or timing resolution, or we may as well decrease the microscopic detail of our description. For example, in a model of eutrophication, we shall reduce the scale to a microscopic detail of phytoplankton growth that is, of course, relevant for a detailed description. So in this context, phytoplankton growth is seen as a submodel that is acting on a lower hierarchical level on the eutrophication model. But if you want to describe consistently the process of eutrophication, you shall also include into your model some forcings that comes from the upper hierarchical level. For example, you shall also include submodels describing nutrient generation. We will see some example of these. In particular, we will discuss nutrient generation models that are models that apply to larger spatial and timing scales. But we will also describe microscopical detailed models like those linked to algal growth or phytoplankton growth. that describe processes that happen or pertain to lower trophic level or to lower hierarchical level. So the point is finding the right hierarchical level means also including or finding where your model is placed in a hierarchical scale so that you're sure that you will include lower scales that are necessary for the detailed descriptions, but also you shall include a higher scale, higher hierarchical scale that are as well necessary for a complete description or for a consistent description of the system. How do we make conceptual models? There are several tools for building conceptual models. Classically, we start with verbal descriptions. For example, I have noticed that the ditch near to my field produce a bad smell. How can I do that? How can I understand which are the processes involved in these events? So this is a typical problem of eutrophication. So you start by describing the situation verbally. There are lots of nutrients. I see that when I fertilize with manure my fields, the subsequent seasons, growing season, I found that the ditch that is collecting the water runoff from my field is plenty of algae. Then the second step is that of translating the verbal description into images. So please forgive me, I draw. Forgive my terrible ability of drawing. For example, I may say, okay, I have an agricultural field and I realize that from the surrounding landscape, there are some flows of nutrients that are entering into my agricultural field. So I start making really bad drawing or sketches, images, describing what's happening. So the focus is the agricultural field, is an example, of course. I realize that my agricultural field is impacted by a relevant nutrient load coming from the surrounding landscapes. And as a consequence, I observe that the water that is collecting, the ditches that are collecting surface runoff water from my agricultural field become eutrophied. Once that I have described verbally the situation, and then once I have introduced some kind of sketches, I am able or I am ready to start a more sophisticated way of conceptualization. For example, that is that of drawing box models. For example, I may individuate a box and say, one variable is phytoplankton. Another variable in my model is, for example, nutrient loads. I realize that nutrient loads have an effect on phytoplankton. But when I realize that phytoplankton dies and there's an effect, for example, and we may introduce another variable that is the bottom or sedimentary or bottom part of the ditches, and so on. So you may recall what we have already seen, this way of schematizing processes. We have called it the box and flow schematization. So the next step after the drawing of images is that of translating your images into a box and flow models. That is a practical way of describing the interactions between the state variables Now you understand that at this point you are introducing the list of state variables, as for example, phytoplankton or nutrient loads or the temperature as a forcing function. These are all forcing variables or external variables or state variables that describe my systems. But at this time, I'm also starting to introduce some kind of functional relationships between the state variables, and these functional relationships are described into my box and flow model as arrows. So the first step in the conceptualization of mathematical and in particular an environmental model is that of building a box and flows or flows and compartments model. At this point, we may immediately decide which part of the model are white box, which part of the model are black box, which part of the model are gray box. So you may remember that we introduced the idea of black box and white box model, or black, gray, and white box models. We call white box model those models for which we can explicitly introduce mathematical relationship describing the processes linking state variables. We instead use black box models when we do not have a hint about mathematical relationships, but we know that some kind of relationships appear. So what we can do is that we can derive statistical relationships between the in and out, or between different state variables. Once we have built a box models, you may recall that we are ready to translate these box models into arrays or matrices, matrix models. We said that matrix models are linear descriptions of a system, but anyway, this is the starting point that allows us to build a conceptual model of a system. How do we translate box models into a matrix model? We build what is called an adjacency matrix. An adjacency matrix is a matrix that is made of zeros and one, while you will have a one if there is an interaction between the state variables, or you will have a zero if no interaction exists at all. Instead of using one and zeros, you may use probabilities describing the probabilities of an event flow of some kind of media from one state variable or from one compartment to another compartment. So we are starting to place numbers also on the flows. Another interesting example of box and flow model may be found for those of you that are comfortable with the programming language in flowcharts. Flowcharts are a description of processes in which you introduce exactly the same abstractions by describing, for example, storages by using boxes, and you describe exchanges between different storages by using arrows. So again, we are in the box and flow. We are using the box and flow description. I recall you, just for a matter of information for you, that in MATLAB, that is the programming tool you are supposed, or I will try to make you employ for building your first mathematical model. In MATLAB, there is a very interesting tool that is called Simulink, that is exactly a way of translating your conceptualization into a box and flow chart model. There are this kind of conceptualization is found ubiquitously in ecology. For example, it was Odum. But in 1984, Odum is one of the fathers of theoretical ecology, but introduced an energetic scheme what allowed him to translate his conceptual modeling into some kind of more computable, calculable descriptions. For example, he uses different symbols, for example, hexagons for identifying state variables, or this kind of symbols for identifying processes, or this kind of symbols to identify storages, and sinks, a box to identify functions. And by this kind of schematization, for example, here you have an example of nutrient, a function describing nutrient loads. Nutrient loads act onto the process, so onto a passive storage, sorry. The passive storage describes the changing in dissolved nitrogen and dissolved phosphorus. These are described as processes, and these processes act on the process of algal growth, phytoplankton growth. So this chain of processes act on the state variable phytoplankton. The advantage of using this schematization is that this schematization is quite general. We can build a kind of electronic flow chart. The symbol have a mathematical meaning, so mathematical implicit meaning. For example, in the case of passive storage, this means that is only an input element in which a state variable may simply be increased or stored. And then by building this kind of schematization, you have also information on the hierarchy of different processes. In this schema, for example, you have that nutrient load generation hierarchically is higher, belongs to a higher hierarchical level than the eutrophication process. So nutrient generation belongs to a higher hierarchical level. Okay, in ecology, generally, the currency that is seen flowing into these boxes may be energy or mass. Energy meaning, for example, joule per unit biomass per unit time, so flows of energy. Mass may be milligrams of something, for example, milligrams of nitrogen per unit time per unit biomass. It is striking the fact that the parallel between ecological and economic model may be easily obtained by using the energetic currency. But of course, you may understand, or we may anticipate that currency is a matter of choices. So it is the model that will choose the most appropriate currency. Moreover, you should recall that we have seen that there is an easy way of passing from energetical currencies to mass currencies, and this passage is obtained by employing the conversion coefficients that we have seen a couple of lectures ago. By employing this kind of schematization, we may describe quite complex systems. For example, in this schema, we are describing a eutrophication model in a lake. So we have, you may recall that the lake may be subdivided into at least three parts: the epilimnium, the upper part of the water column, the hypolimnium, lower part of the water column. The thermocline is the line subdividing epilimnium from hypolimnium, and a third part is sediments, what's happening in the bottom. So the modeler here has introduced some state variables. For example, dissolved phosphorus is a state variable. Phosphorus in algae is a state variable. Detritus phosphorus, phosphorus in zooplankton. The same applies to the hypolimnium. So there is a spatial subdivision between the epilimnion and the hypolimnion, and a spatial subdivision between the hypolimnion and the sediments. The arrows connecting the different state variables describe processes. For example, if you look at the arrows that is described by the number 1, you will see that 1 is the process of uptake of phosphorus by algae. So 1 is a process of transfer of phosphorus from the dissolved quota in the water column to algae. So this is a process of algal growth. Again, for example, process 2 is grazing by herbivorous fish. So this is a passage of phosphorus from phosphorus in the algal pool to phosphorus in fishes. But we have also processes describing spatializations. For example, let's give a look to process 12. Process 12 is exchanges of phosphorus between epilimnion and hypolimnion. Process 13, settling of algae, epilimnion from epilimnion to the hypolimnion. 14 is settling of detritus. Sorry. Detritus. So okay. This is detritus phosphorus, detritus phosphorus. Okay, there is a lacking of number. So this is the 14th process. Detritus that is passing from the epilimnion to hypolimnion by crossing the thermocline. So you see that we are starting here to convert our conceptualization, that is our verbal description, and our drawing by identifying the elements that will become the key elements of my mathematical model of the ecosystem, in this case, a lake. I recall you that the 5 elements of ecological model are state variables, constants, universal constants, parameters, flows, and forcing function. For example, in this kind of schematization, you might also include 21, that is precipitation, that brings some kind of phosphorus. This is atmospheric deposition of phosphorus, but as well, you may include outflows that are flow out of the system, or, for example, fishery, that is, this is fishery, it is phosphorus, but it's taken away from phosphorus, the process of fishery. This very general schematization, the conceptual schematization compartment of flows is a very powerful one. Very powerful, very general. You may employ this kind of schematization in almost all your building of conceptual models, conceptualization. So the assumption here is that a network of flows and compartments is adequate for describing your system. So you have a system that is bounded from a boundary. Inside your system, you fix some state variables. In this case, 1, 2, 3 refer to state variables. When you describe the exchanges between the state variables, for example, J31 and J13, I recall you that these exchanges are synced exchanges, meaning that J13 is media that is going out from compartment 1, entering into compartment 3, while J31 are flows that are exiting from compartment 3 and entering into compartment 1. So the symbol JIK describe the flow originating from E, I, and entering in K. This way of representing a conceptual model is very interesting because also it allows us to calculate from immediately some very general indicators or characteristics of a system. For example, one of these characteristics, that is the total flow, total system throughput, that is given by the summation on both indexes I and k of all the flows. So here you are summing all the flows. This quantity, what is called total system throughput, it is an indicator of how much the system is working in terms of material or media exchanges between the compartments. So it is a kind of indicators like the temperature that tells the modeler how much the system is working. We will see that with kind of schematization, by this kind of schematization, we can calculate several indicators that are of interest for the evaluation of the quality of a system. This way of schematization of trophic exchange or this way of translating the conceptual modeling, the conceptual model is very general, and we made it as complicated as we want. For example, as we will present in one of the latest lecture, we will introduce a software that is called EcoPath. That is a software that describes the exchanges of material in trophic networks. Trophic means nutrients. So a trophic network is a network of exchange of nutrients. In this example, we have modeled the network of exchanges of nutrients in the Lagoon of Venice, in a very confined area of Lagoon of Venice that is called Palude della Rosa. This is the mean annual model referred to year 2001. You see that we have several state variables, like, for example, phytoplankton, plankton detritus, benthic detritus, benthic algae, macroalgae. These are the lowest trophic levels, so 1. If we go to a higher trophic level, when we find microzooplankton, Lysa spinatus, but it's a fish, macrobenthic suspended feeders, these are all animals that pertain, crustaceans, that pertain to the second and the third trophic level. Carcinus means la Mazaneta. It's a crab, Carcinus. Gobius of Icephalus is a larger fish. So we are going up and we are arriving up to, for example, carnivorous species. But also we may also insert birds on this kind of schematization. This way of describing the network of exchanges of nutrients in a trophic network is very filled with information. For example, you have first information, that is the displacement among the different trophic levels of the different species into your system. So the lower trophic level are those of the primary production, like phytoplankton. So primary production is always trophic level 1, the lowest. And then going up with the trophic levels, you find organisms that feed on trophic level 1. If you go upper, you find organisms that are feeding on trophic level 2, and so on. Here, the arrows, sorry, the lines represent path of exchanges of media. Inside the boxes, you have the storages. This is B refers, for example, to biomass. While P refers to production and TL refers to trophic level. No, sorry, TL is another indicator, it's not trophic level. The important is B biomass and P production. So production is a flow, biomass is a storage of matter. So we see immediately that the dimension of these boxes is proportional to the product between biomass and production, that is called Q. So Q is an indicator of how much biomass of a given species is present in the trophic network. Okay, we said that living systems are natural systems, and nature, we said, is complex. We already seen a kind of uncertainty principle by saying that it is not possible to describe the reactions of all species in all possible combination of the forcings. So there is a kind of uncertainty principle. All components, all processes of an ecological system cannot be described all at once with an arbitrary accuracy. So this is why we need to find a rate trade-off in terms of the complexity of our description. So the trade-off is between knowing all of nothing and nothing of all. So if you try to concentrate on all the elements, then you end up with a very small knowledge. If you try to reduce your pretension, then you may find the right trade-off. A way of measuring this trade-off or uncertainty is a kind of uncertainty principle, like the principle of Heisenberg. We may say that the inverse ratio of the product of the uncertainty on the number of elements times the accuracy. So if we increase the number of elements in the systems, or if we increase the accuracy, then we have that this number tends to diminish, but this lowering has a kind of lower boundary that is represented by an even if smaller constant, like K. It is exactly the parallel of when we said that the time, the product of the uncertainty and momentum time, the uncertainty of the position is always bigger than a smaller constant h. You may recall this is the uncertainty principle in quantum mechanics. There is an analogous in ecology. So we have a limit, what is the limit of including the largest number of elements into a system and the largest accuracy in the description of the elements in the system. So we end up by saying that ecological systems are generally complex. Conceptual models can be made arbitrarily complex, as I showed you the model of the trophic network of the Palude de la Rosa and the Laguna of Venice. I recall you that these are 1, 2, 3, 4, 5, 6, more than 20 state variables and a lot more of flows, so processes, relationships between state variables. So we may say that mathematical models are, conceptual models can be made arbitrarily complex. Mathematical models, of course, are simplification of the systems. We may say that are caricatures, in which the modeler focuses his interest on a peculiar aspect. The degree of simplification of the systems or model complexity is determined by the availability of data and knowledge of the processes. So it depends on the understanding of the modeler of a system, understanding of the system by the modeler, the level of complexity of the description. The iterative process of simplification is conducted first on the conceptual model. This is why it is important to start from the conceptualization. The base model as introduced by Ziegler in 1976, is almost never applicable because it is a model that considers all the input-output relations, and it cannot be generally mathematically treated, and it is not manageable in terms of CPU demanding. So let's switch to a way of describing model complexity. Now we're going to introduce an operative way of defining and measuring the complexity of mathematical model in terms of our schematization as box and flow models. I'm sorry for the quality of the picture, but if you download from the Moodle webpage the chapter 2, that is a PDF of fundamentals of ecological modeling, you will have this picture with a higher quality, I think. In any case, these are 6 possible description, or 6 possible models of a system that is constituted by 10 state variables, 1, 2, 3, 4, 5, 6, 7, 8, plus input plus output. So we have 10 state variables, and we include also, strictly speaking, we have 8 state variables, and 2 forcings that are input and output. We may change the configuration of our model by adding or taking away some kind of flows. In particular, this model, 10 state variables, we say, okay, 8 state variables plus 2 forcing functions, input and output. We have suspended solids, water, fish, benthos, pore water, bottom sediments. Input and output, as I told you, 9 is detritus, plankton, benthic fish, and seabirds. Of course, we are not specifying here which is the currency, but for example, you may imagine that the currency in this case might be phosphorus or nitrogen in the different quotas or in the different state variables. So we have T1, T2, T3, T4, T5, T6, 6 different configurations of the model. By looking at this configuration, we build what we may call an adjacency matrix. For example, for model T4, I want to go to this model. The adjacency matrix is the matrix here. In this matrix, we have the 8 state variables, 10 state variables plus input plus output. The interaction, so we will have a 0 in the adjacency matrix if there is no interaction, and a 1 if there is interaction. So this is a way of describing how a system is connected, or how the elements of a system are connected among others. There is a slight inconsistencies because here I say that we have 12 state variables. Yes, input plus output. No, it's okay, 12 to 12. So given that we have 12 elements, this matrix is a 12 by 12, 144 elements. So a first evaluation of a complexity of a model may be found by employing the adjacency matrix, and by, for example, calculating the number of ones that are present in the adjacency matrix divided by the total number of cells in the matrix. In this case, we have 28 ones divided by 144. The direct connectivity, that is the first indicator what I might calculate, is exactly 0.194. Direct connectivity is equal to the sum of the ones appearing in the adjacency matrix divided by the square of the number of lines or columns, because this is a square matrix. Okay, so the first indicator of complexity of a model is the adjacency matrix. Please note that here you have simply a topological description of a system. So who is connected with whom? You have 1 if there is a path linking the two state variables, and 0 if no path is available. Let's look, for example, a different example. This is another model. Here we have 8 state variables: suspended solid water, fish, bentos, pore water, bottom sediments, input and output. And this is the adjacency matrix calculated for the model M4. Again, we count the number of ones. In this case, the state variables are 8. So we divide this number by 64, that is 8 by 8, and we obtain a connectivity, direct connectivity of 0.234. Again, direct connectivity, I recall, is equal to the sum of ones divided by the square of the number of lines. Direct connectivity is a first essay of evaluating the complexity of a model, but we may employ a little bit more sophisticated indicator. The second very important indicator, what is indicator that is customarily employed in environmental modeling, is the so-called Bosselman index, or Bosselman measure of recycling. How do we calculate the Bosselman index? We start by the adjacency matrix. In this case, it is 8 by 8. 2, 4. Yes, this is the model M4. See? Again, we start from model M4. This is the adjacency matrix for model M4. And we count that there are 19 ones in this adjacency matrix. Then we start by doing the square of the adjacency matrix. This square is simply a product in the algebra of matrices. So this is a row by column product. And we calculate the square of the adjacency matrix. And we recast the values on this square matrix by putting a 1 if we have a value different from 0, and the 0 as in the other cases. So if you have a value different from 0, we put 1, and if you have 0, we leave 0. Why these are not ones? Because the square of this matrix, the square of the adjacency matrix, from a topological point of view, is counting how many pathways of length 2 are present in the network. So this matrix has ones if there is at least one pathway of length 2 connecting two compartments. Let me see if I can explain this by making one of my table drawings. For example, if we identify a matrix of 4 compartments, this is the case 4 by 4. Then we may have arrows, 1, 2, connecting the flows, connecting the different compartments. You may understand immediately that if a unit of media shall pass from compartment 2 with 1 to compartment 4 with 1, there is a two-step pathway. So from compartment 1 unit, from compartment 2, 1 unit of media has to pass to compartment 3 and then pass to compartment 4. So there is a two-step connection between compartment 3 and between compartment 2 and compartment 4. So the square matrix counts the number of two-step connection between the different compartments in the network. So you may understand that the square of this matrix is another indicator of how much the network is connected or how much the material is cycling into the network. Again, you may count the numbers of ones. You may make a summation between the number of ones in the matrix A and the number of ones in the matrix A squared. You obtain 39. Then you, of course, you can go ahead and make the cube of the adjacency matrix. So here you're counting if there is at least one pathway of length 3 between the compartments. You have a 1 if there is at least one. You have 0 if there is no connection. Again, you count by 1. You go on by making the powers. When you realize that subsequent powers are all equal, so in this case, A5 to A8, so the 8th power of the adjacency matrix are all equal, then you stop and you sum after the third matrix, that is called the reachability matrix, and you sum all the ones that appears into your matrices, and you divide by the cube of the number of lines. This indicator is called the Bosman recycling index. The Bosman recycling index is the sum of ones appearing in the adjacency matrix and subsequent powers up to a power 8, of course, because we have 8 rows and lines, divided by the cube of the number of rows and lines. This indicator is much more sophisticated in terms of evaluating the complexity of your ecological model, because besides describing a simple topological characteristic, that is the direct connectivity, so who is connected with whom with a direct jump, you here are including also an evaluation of how much in general the network is connected in terms of recycling. So how much is the ability of a network to exchange media. A more connected network or more recycling network, it is a more complex model or a more complex network. So this is a direct measure of the complexity of your model. How do we employ these measures of complexity? This is an example. For example, we are calculating direct connectivities for models M1 to model M6, direct connectivity from model T1 to model T6. This is the direct connectivity, and instead the second column is the Bosman recycling index. We have two cases. One case in which we assume that there is no internal recycling in the single compartments of a network. This means that the value of the diagonal are 0. And these are cases in which there is complete recycling into separate compartments of a network. So these are cases in which the diagonal values are 1s. You obtain a set of indicators of direct connectivity. direct connectivity, sorry, and Bosman recycling index, the second column. I recall you that with C, that is the Bosman recycling index, it is with C here. So how can we employ this indicator to choose the appropriate level of complexity of my model? We look at both models, but by increasing the complexity in terms of adding state variables, if you want, compartment, adding flows, so relationships between state variables, we have a significant increase in the indicators. For example, let's give a look at the Boltzmann recycling index for model Nces. You see that going from model M1 to model M2, we have a dramatic jump of the Boltzmann recycling index. Boltzmann recycling is quite stable up to model M4, and then the next significant jump is to model M6. This means that if I increase the complexity of my model going from model M1 to model M2, it is significant, interesting. If going from M2 to M3, I'm not increasing very much the recycling, so maybe I should stay on model M2, but passing from model M2 to model M5, I have a significant increase of recycling. Same applies to model Ts, for example. Here it is a little bit more sophisticated because you have to go to the first decimal value of the recycling index, but anyhow, here you have 0, 06, 14, 17 increase, 24, so this is a significant step on, passing from model T3 to model T4. Passing from model T4 to model T5, you have another important increase, 32, but passing from model T5 to model T6, the increase is not so significant. So the idea is that you can employ these indicators, direct connectivity, and Boltzmann recycling index, to decide if the complications that you're adding to your model or to the box and flow descriptions are worthwhile including or not. If you look at the numbers, you may notice that the Boltzmann recycling index is a little bit more sensitive than the direct connectivity in distinguishing between different network configurations. So first question, the question, how do I measure model complexity? The answer is by calculating the Boltzmann recycling index on the basis of the adjacency matrix. There is another similar way of measuring the model complexity in terms of model performance. You employ for doing this the so-called buffer capacity. Buffer capacity is the inverse of the ratio between a variation of a state variable as a consequence of variation of a forcing function or of a parameter. For example, we may notice that there are several buffer capacities depending on the type of model that you are employing. The purpose of the model should indicate which is the buffer capacity to choose. For example, in a eutrophication model, which phytoplankton is one of the phytoplankton density is one of the relevant characteristics describing the quality, status quality of your freshwater system. Nutrient loads, for example, phosphorus load is another relevant characteristic describing the effect of the surrounding environment on your local ecosystem. Then you may introduce a buffer capacity in terms of how much varies the value of a state variable as a consequence of the variation of the forcing function. For example, you plot the state variable as a function of the forcing function. And if you analyze this curve, you see immediately that in this area, there is a significant variation, not significant variation of the state function. So an increase in the forcing function in this range is not changing the behavior of the model significantly, while in this range, for example, a changing of a forcing function in this range may cause a dramatic change of the value of the state variable. So what you will say, or what you may say by employing this analysis, is that an increase of complexities but changes the behavior of a model from this point to this other point is worthwhile because you have an apparent macroscopic variation of the behavior of a model linking to a small variation. You see here, with a large variation of a forcing function, you have almost no variation of a state variable. Here, with a small variation of a forcing function, you have a dramatic variation of a state variable. So an increase of the complexity of your model that brings the behavior of the model to jump from one state to another is a significant increase. So it is a worthwhile in terms of growing the complexity of your model. Another way of employing buffer capacity to evaluate the complexity of the model is, for example, that of evaluating how the buffer capacity as a whole changes as a function of a number of state variables. For example, you may say that 1, 2, 3 state variables are significant increases in state variables in terms of changing of a buffer capacity, while going from 4, 5, 5, 6, 7, this last part, 3 increase of number of state variables, it is not significant. So instead of employing, for example, 1, 2, 3, 4, 5 state variables is a reasonable, but adding 6, 7, these two more adding that increase the complexity of your model are not significant in terms of the variation of the behavior of the model. So the buffer capacity is a way of measuring the responsiveness of your model to the variation of various aspects, for example, parameters, forcing function, adding number of state variables, and so on. So the second way of evaluating the complexity of an ecological model is that of employing buffer capacities in terms of evaluation of the responsiveness of your model to changement to the structure of a model. So when I will ask you which is a way of measuring model complexity, you will answer the Bosmer recycling index and the evaluation of the buffer capacity as a tool for evaluating the responsiveness of the model. Then we shall finish the lecture of today by introducing the concept of verification of the model. We have already said something about that. We may say trivially that a model is verified if it behaves in the way in which the modeler wants it to behave. Okay, it sounds trivial, but in your experience of models, you may discover that you build a model and when you discover, you realize that your model is not behaving as you expect. What does it mean? First of all, it means that the model has to exist, should exist. So there should be equations. You should have reasonable values of the parameters, and you should have some experimental data to verify if a model behaves as expected. If a model does not behave as you expect it to behave, this means that there is some kind of um, internal structural error in the building of a model. For example, one check is that of checking the verification by error control. You expect that the difference between simulated and observed values, this is why you need here that some experimental data exists, the difference between simulated and observed values in average should be 0. Means that, let's say, if your observed values are dots like this, then I am expecting that my model the behavior of my model should place somehow here. If this is not the case, for example, if the output of my model is doing something like that, then there is, of course, what is called a systematic error that is causing a non-neglectable deviation of the behavior of the model. Then the model should have internal logic. We have always said also, we said something about this, about internal logic, by saying that, for example, I'm expecting that my understanding of ecological processes or physical, biochemical processes at play are consistent. For example, I'm expecting that if one state variable of my model is BOD5, so biological oxygen demand over 5 days, then I'm expecting that an increase in the load of BOD5 corresponds on a decrease of dissolved oxygen, or an increase in the temperature corresponds to a decrease of dissolved oxygen, or an increase in nutrient loads corresponds to an increase in chlorophyll A. If these checks are not positive, this means that your model is missing some internal logic. So you're missing to include into your models some key aspects of the process that you want to model. And then the final check you should do has to do with the internal stability. Again, a model is said to be long-term, to be stable in the long term if it behaves, its output behaves in a way more or less constant. Instead, if you have dramatic transients, which, for example, the output of your model is derivating toward infinity, then your model is not stable in the long term and cannot be said to be verified. Please notice that these are not so trivial checks, meaning that when you're building a mathematical model, you are adding an arbitrary high level of complexity, but may make the things very difficult to follow in an explicit way. So it might be difficult to understand which changes, for example, in the forcing functions have caused a dramatic deviation of the behavior of your model. This is why these kind of checks are the typical checks, are the customary checks that should always be carried by the model in the process of building a mathematical model. So no systematic error, simulator minus observed in average is equal to 0. The difference between simulated and observed data in average is, should be 0 or close to 0. So no mutual correlation. Internal logic, so the process, the model responds according to your understanding of the processes, and the model should not display catastrophic behaviors. Instead, should display a long-term stability. Okay, I think we shall stop here today. If you have any questions, I stay in class for 10 minutes, and then I close the classroom, and we go to next Tuesday. Sorry, to next Monday, Tuesday. Signori, arrivederci, chiudo la classe.